Okay, hello everyone. So let's get back into the limited reaction questions. So let's just apply this to an in-class example. So fireworks. So the white light emitted during a fireworks display is produced by burning certain elements, and the bright white light is actually characteristic of magnesium. So very, very cool um, chemical uh, a chemical phenomenon. Okay, white light is so bright that when my father was growing up, his brother liked to play tricks with chemicals sometimes. So he burned magnesium in his basement, and the white light ended up being so bright that I didn't get temporarily blinded. My dad, so he kind of resents his brother for that. But it's a very cool phenomenon. Um, um, so we may see this in lab, but I don't. I'm not sure if we will. We won't be actually burning things, but yeah, I don't think we'll be burning anything, unfortunately. But for these displays, for fireworks, it's pretty cool. And if you ever set off a firework, you can see the dangers that are presented based on like these kinds of explosions and the uh, the nice visual effects. So it's a very exothermic or very energy intensive process. Okay. All right. So magnesium metal burns rapidly in air to form magnesium oxide. So that's a chemical reaction, and the result of this is the energy release is in the form of the white light that we see. Okay, the reaction gives off an enormous amount of energy and is used in both flares and fireworks. So a typical flare, they use either potassium or strontium to get that red color. So um, that's pretty much the source of the red light. Okay, so what mass of magnesium oxide is formed when 10 grams? So when 10 grams of magnesium react with this 10 grams of oxygen. Okay, so let's write the balanced chemical equation first. Okay, so we know we have magnesium metal, so we're going to write magnesium solid, indicate it's a metal, plus oxygen gas, so O2. So when we say in air, we mean with oxygen. So that's a term to mean with oxygen. If it refers to anything else in the air, we would say we would specify what. But if we say in the air, it's usually because of oxygen. Nitrogen gas doesn't usually react with anything, so it doesn't really oxidize things. So the main suspect for if something happened in air, like your reaction went bad in air, it's because it reacted with oxygen. And that's what happens, when food spoils, right? It's because of the air, the oxygen in the air. Okay, so it forms magnesium oxide and gives off heat, or let's say plus light, which is heat in our example. Okay, heat in this case. Okay, so first thing is first we have to balance the chemical reaction, and we notice here that there's not as much oxygen atoms on the product side of the reaction, so we should balance the oxygen first. So let's put a 2 here, and then we can see on the left we would need 2 magnesiums, and we put 2 in front of there, and that makes the reactions balanced. Okay, so magnesium oxide is usually a solid, so the debris here would probably be magnesium oxide as a result of this experiment. All right, so we wrote the balanced chemical equation now, so let's go to step 2, determine the limiting reactant. Okay, so to determine the limiting reactant, we need to calculate the moles of each first. So 10 grams of magnesium, so the molar mass of magnesium is 24.31 grams. Magnesium per 1 mole of magnesium. Okay, so if we carry out that calculation, we get 0.411 moles magnesium. Okay, so that cancels out the magnesium, and we end up with moles. Now, let's talk about oxygen. So we know 1 mole of oxygen is equal to 32 grams of oxygen. So grams of oxygen will cancel, and we get 0.31 mole oxygen. Okay. So a common misconception is that students will choose the moles of the reactant with the lesser amount of moles as the limiting reactant. Now that's a good rule of thumb if your chemical equation is in a 1-to-1 ratio of the reactants. But if we scroll up here, we notice that for every mole of oxygen, we require 2 moles of magnesium. So it's probably you're probably going to get a limiting reactant that has twice the amount required. So it's most likely that magnesium is going to be the limiting reactant here, but let's do the calculations to find out. So you can make an assumption based on what you feel, but you need to do the math and show evidence to back up your claim. So we can't just willy-nilly say, oh, it's probably magnesium, because there's twice the amount required for it. We need to be sure. So for this, let's demonstrate how much mole of product can be made from both our reactants. So we have 0.411. So we use 3 sig figs here. So magnesium oxide, our next example. So we notice that we have, so in our chemical equation, right, it says here 2 magnesium moles of, so we need 2 moles of magnesium to react with 2 moles of magnesium oxide. So our ratio is going to be 1-to-1, right? So 1 mole, if we simplify it, so 1 mole of magnesium will produce approximately 1 mole, well not approximately, sorry, 1 mole of magnesium oxide. Okay, in terms of magnesium. Now let's write the ratio for oxygen. 0.313 mole of oxygen. We will require, going back to our balanced equation, 1 mole of oxygen. So there's an imaginary 1 here. So we're going to have 1 mole of oxygen per 2 moles of magnesium oxide. So 1 mole oxygen to 2 moles magnesium oxide. Okay. So I think it's pretty clear, based just by looking at the setups for the calculations here, it looks like we're going to produce a lot more magnesium oxide with oxygen and even less with magnesium. Okay, so in this case, we have our moles of magnesium will produce 0.411 moles of magnesium oxide. And then oxygen will produce 0.626 mole of magnesium oxide. So since we can only produce 0.411 moles of magnesium oxide with magnesium, that is going to be our limiting reagent. So this will be our limiting reagent. Limiting reagent is magnesium. Okay? And that's because once we produce that much product, magnesium will no longer be there. So it'll be converted all to magnesium oxide. So the reaction will just stop. And that's why when you eventually, once you light up all the magnesium and oxygen, the light from the reaction will just disappear. So it'll be a short-lived reaction. Okay. Okay, so that's how we determine the limiting reagent. Okay, so in every chemical equation, when you know both amounts of all the reactants, you need to determine the limiting reagent. If you don't, you will not arrive at the right answer, and you won't get all the points for like an exam or a homework question. Okay, so when you have both finite values for both reactants, you must calculate or determine the limiting reagent. I just want to get that crystal clear across to everyone. Okay? So now usually we say, oh, what's the yield we can make? Or what's the mass of product that we can make from the limiting reactant? Reagent. So sorry, reagent and reactant is pretty much the same term. They use it interchangeably. So just know in my class, it means the same thing. Okay? All right, step 4. Calculate the mass of magnesium oxide that can be made from the limiting reagent. Okay, so now we need to know the molar mass of magnesium oxide. So the mass of magnesium oxide is, so we're going to take MgO equals 24.31. So this is magnesium plus 16.00, that's for oxygen. And if we add these together, we will get 40.31 grams per mole. Okay, very well, 40.31 grams per mole. So now let's take the amount of product that we can make in moles, 0.411, and we know that for every mole of magnesium oxide, we just calculated it, our molar mass there, so it's going to be 40.31. So in this case, we get 16.6, I believe. So let's just double check. 0.411 times 40.31. Yeah, so we get 16.6 grams of magnesium oxide. So even though that's not a lot of moles of magnesium oxide, it's still a fair amount of in grams. So even though it's 0.4, even though we don't have moles and whole numbers, it's still a lot of mass in terms of weighing it out. So in this case, this will be our theoretical yield. So our theoretical yield is I'll go over it in a minute. So this is what we call the theoretical yield. So that's the total amount of product that we can make in a reaction. Okay. Now, let's do something else here. Let's go over, calculate the excess mass of leftover reagent to demonstrate that mass is conserved. Okay, so, sorry, I should have scrolled down first. Here we go. So we're going to calculate over the leftover mass. Okay? So we've used... So first off, we have 0.411 moles of magnesium, right? And we know that for every 2 moles of oxygen, 2 moles of magnesium, my apologies, we are going to get 1 mole of oxygen, right? So this will tell us how much oxygen is consumed. Okay? So this will give us 0.206 mole oxygen. So this is how much oxygen will be consumed. Okay? And if we multiply this by the molar mass, we will get 6.59 grams of oxygen. Okay? So let's just double check that here. 0.206 times 32, the molar mass of oxygen. So we get 6.59 grams. Let me just rewrite that a little bit. Sorry. There we go. Okay. So to calculate the amount of leftover oxygen, we're going to subtract this number of moles from the total moles we had at the start. So if we go back up, we had initially 0.313. So we're going to say 0.313 minus 0.206 gives us 0.107 mole O2 left over. Okay? So then we're going to put that excess here, 107 times 32.00 grams of oxygen for 1 mole of oxygen. And we get 3.42 grams of oxygen left over. And now if we combine these two numbers, right, 6.59 plus 3.42, that's roughly around 10 grams, right? So 6.59 plus 3.42 is approximately equal to 10.0 grams. Okay, so mass is conserved there. You see, we consumed some oxygen, but then we get a leftover amount of oxygen because that's the excess reagent. So our mass is conserved here. So 10 grams here, and then if we scroll up here, we see we started out with 10 grams of oxygen here, so the mass is conserved. Now, we don't get any excess magnesium because all of it was consumed. So in every chemical reaction, there's always going to be a limiting reactant and an excess reactant, unless you add exactly equal amounts. But usually that's usually one's the limiting reactant and one's in excess. All right. So for the last part, let's cover these two examples, and then we'll call it the end for today's lecture. Percent yield. So percent yield is actual yield over theoretical yield. So let's go over some of those terms. So theoretical yield is the amount of product in grams determined through stoichiometry calculations. So it's basically all the work we just did. So that's the total amount of product you should get if in a perfect scenario. Say you can you can isolate or collect all the mass of product without any loss. That's a perfect situation. Of course, sometimes you can get 100% yield, just because the reaction, that's kind of like a great reaction, something that doesn't happen all the time. Your actual yield is the amount of product in grams that was measured in the lab, obtained after experiment is complete. So after we do an experiment, we isolate the product, and that's basically the mass of that is your actual yield. Okay, so let's do an example. So calculate the yield of the reaction if only 12.3 grams of magnesium oxide was obtained at the end of the experiment. Okay, so let's list what we have. Actual yield, 12.3 grams. Okay, magnesium oxide. Theoretical yield, our theoretical yield is 16.6. So going off this equation here, we know percent yield equals actual over theoretical. and we multiply that fraction decimal by 100. Okay, so this will be equal to 12.3 grams over 16.6 grams. Grams will cancel out here, and then you multiply by 100, and we get 74.1. So that's a pretty decent yield. So 74.1%. So that's pretty decent. So that's the percent yield calculation. You will do this in lab. So we'll calculate percent yield. So you actually want to get product in the lab. So you should try your best to get as much product as you can. And, don't feel bad if you don't get like the highest yield. With chemistry, there's some bit of luck, but a lot of it is technique. Technique and how you pretty much carry out many of the procedures in the lab. So that's a big part of it too. And another part of it is just the reaction in general. Is the reaction a good reaction or is it a poor reaction? So not all reactions are created equal. Some work well, some don't work as well, and some are just amazing and gives you product every time. So it's kind of hit or miss sometimes. Okay, so let's just go over this last example here, and we'll call it a day. All right. So let's go over limiting reactants one more time. So this equation, assume that 4 grams of iodine are allowed to react with 4 grams of magnesium according to this chemical equation. Okay. So as you see here, the chemical equation is already balanced for us. So now we just need to figure out the limiting reactant based on the moles. So 4 grams of iodine. So 4 grams of iodine. Okay. So for iodine, let's just write here. So iodine's molar mass is equal to 2 times 127. I believe it's 0.4 grams. Okay, and that will give us 253.8 grams per mole. And we already know magnesium's, right, is 24.31. So now let's do this setup here. So for 1 mole of iodine, so it's I2, we get 253. Actually, I don't think it's 127. Let me back up. I think it's 126. My apologies. Or maybe it is 127. Let's see. 126.4 times 2. Yeah, actually it is 127. Maybe that's right the first time. Or not. Interesting. All right, guys, so let's look at our periodic tables for real now. Okay. All right. So sometimes we just forget. Oh, okay, so it's actually 126.8. My apologies. That makes more sense. Okay, so yeah, that actually makes more sense now. 126.9 times 2. Yeah, sorry, 26.9, not 8. Okay, and we get that 253.8 grams of iodine. All right, so when we do that, we will get 0.0158 moles of iodine. Okay. Now let's convert 4 grams of magnesium. 4 grams magnesium. So we know that 1 mole of magnesium is equal to 24.31 grams of magnesium based off the periodic table. And if we divide that number 3.1, we get 0.0. No, sorry, not 0.0. 0.0 165. 165 moles of magnesium. So if we compare, so now if we compare how much moles of iodine we need for moles of magnesium, we see here that 1 mole of magnesium is equal to 1 mole of iodine in the chemical equation, right? So that means we would, for 0.0158 moles of iodine, we would need 1 mole of iodine per 1 mole of magnesium. So this would give us 0.0158 moles magnesium needed. Right? So that means we need at least that much magnesium. But as we can see, we have almost 10 times as much magnesium than iodine. So in this case, iodine here is the limiting reactant. And since this reaction is a 1-to-1 ratio, you can determine the limiting reactant as the one with the lesser amount of moles, because they are in a 1-to-1 mole relationship in the chemical equation. So that's the only time you can say, oh yeah, it's this one, because it's they're in equal ratios in the chemical equation, and it has a smaller amount of moles. So that's the only time. But if I ask you to determine the limiting reagent and show your work, you'll probably want to do this calculation, okay? And in some problems, when you need to find the limiting reactant to solve the problem, you probably don't want to just assume, and you want to go through the steps to make sure you're correct, okay? All right, so that's the end of this lecture. Next time we'll be going over solute concentration and solution stoichiometry. So we'll now take our talk of stoichiometry in solution. Well, the most common way we do chemistry is in solution. So we'll talk about that next. So if there's if you want to read ahead, please go to this link, and it'll link you to the textbook, and you can start reading before the next lecture. Okay, so that's the end of this lecture. I hope it was a little bit of fun. If there's any questions, please let me know. I'll see you next time.